Okay, let's start our last talk of this session. The speaker is Professor Naoki Genra. The title is Reduction by Stages on W-algebras. Please.
Thank you for introduction, and I first thank all organizers for giving opportunity to give a talk and a great conference here. Especially I thank Takebe-san for inviting me here. In fact, this is the first time to invite Beijing, so I'm very happy to come here. So first of all, today I talk about some result on W-algebra. So some Monday and I think it's Tuesday, some people talking about some finite W-algebra, and today let's talk about the deformed W-algebra. So I talking about some affine, finite, but not deformed. I'm sorry, I could not talk about deformed. It's so complicated for me. So this is a joint work with Thibault Juillard. So first of all, I explained some motivation about affine W-algebra because not people are talking about this. So most famous example of affine W-algebra is just the Virasoro algebra. It's just infinite-dimensional Lie algebra generated by Ln, one family, and C. And C is just the central element. And this satisfies the famous Virasoro relation. And this plays a very important role in the two-dimensional conformal field theory, but also has a very nice representation theory. For example, if C acts on the scalar as some representation, it's called the central charge, and it has some nice rational number. It has a nice representation called the minimal series, and satisfies some nice fusion rule, and can compute S matrix by using Fiorini formula. And in fact, in that case, category of Virasoro module becomes a module tensor category. So this means that you can compute Q character, and that is some combinatorics of modular functions. It's very nice. So the natural question is we want to have a generalization of this Virasoro algebra. We want to get somehow some family of such a nice algebra. That is our W algebra. Such a nice example is first found by physicist named Zamochikov. He found in the work of classification of two-dimensional conformal field theory, and it's now called W3 algebra. So it contains Virasoro algebra. In fact, in general, affine W algebra contains Virasoro. It's same as simply algebra contains SL2. So Virasoro is somehow work of as SL2 in the law in W algebra theory. So it means W3. So W3 is a family of Ln. This is Virasoro, but also it contains Sn. But the Lie bracket of Sm and Sn contains the infinite sum of quadratic form of Ln. So this means that this is not Lie algebra. So we need to think about this operator. This is algebra as operator acting on some vector space. So this means we need to define this algebra. We need to fix faithful representation. This requires this algebra should be defined as a vertex algebra. So physicists working so hard, but if and look can now find a generalization of this algebra named Wn algebra. This defines as some kernel of screening charge, and they associate such a screening charge as a root system of type A. So they change the root system to type BCD and then get WBN, WCN, WDN, and so on. So later, Boris Fagin and Edward Frenkel found a nice mathematical definition using green philosophical reduction. The construction, if you take G as simply algebra, they associate affine vertex algebra. It's somehow vertex algebra version of affine Lie algebra. Then they take green philosophical reduction. They get some algebra named WKG. It's called the principal W algebra of G at level K. And if you take G's SLN, this becomes a Wn algebra. So they recover a nice algebra, so it's very nice definition. And if you n equal 2, it's just a Virasoro algebra. In that case, central charge can be written in terms of level K. So that is somehow point. But later, Fagin and also Samikato found an interesting different family of W algebra. It's named W2n algebra. I asked Boris about what is the meaning of 2. he said the second, because he thinks W2M is a secondly important family of W-algebra. That's the reason. So n equal 2, this becomes affine SL2. But n equals 3, it's called the Bershadsky-Polyakov algebra. It's somehow deformation of affine SL2. It's generated by En, Hn, Fn. That is like same as SL2 triple, but also has Ln. And if you compute bracket of Ef and Fn, it contains a linear term of Ln, but also quadratic term of Hn. So this means this is still not the algebra. So this is also vertex algebra. The question is how to define this algebra using more somehow like original WKG, because this does not appear as example of WKG. This problem has been solved by Katsuo and Wakimoto. They introduced a new definition. I mean, they generalize the definition of dream field of reduction. So they think G is simply algebra, in more general, simply superalgebra, and F is taking the nilpotent element. In super case, we assume F is even parity. And then WKGF is defined dream philosophical reduction of affine BKG, but cohomology is somehow generalized, associate choice of F. This is called the affine W-algebra of GF at level K. And if you take F equals 0, this is affine, vertex algebra. But if F is a principal, this recovers Feigen-Flanker's definition. That's the reason the definition, the algebra is called principal, because this corresponding to the principal important element. Yes.
For classical series, now they gave it for argument, right?
Yes.
But for classical, it was Lukyanov and others, right? Was basically known, right?
Yes. Yes. So point is the definition. Physicists define this algebra using screening operator, and the Feigen-Flanker shows that the definition isomorphic to their definition. I mean, they define the cohomology and taking some double complex, and it's isomorphic to kind of some screening operator. Yeah, different definition. Yeah, because screening is somehow difficult to generalize in some cases, but they associate easily. And if you take G as SLN and F is subregular nilpotent element, it's isomorphic to Feigen semi-Kirchhoff algebra. It's very nice. This contains all examples appearing in this slide. And the point is, if this definition approach is somehow good, advantage is if you take M is module of affine algebra of level K, we apply this derivative of reduction, we obtain the module of W algebra. This means this definition makes a connection between W algebra and affine algebra. That is somehow a good point.
Now arbitrary principle and subregular nilpotent elements.
Yeah, now we can choose any nilpotent element. Yeah, in my talk I changed many changes of nilpotent element. Yeah, thanks. Okay, so now we go to our problem. It's called the Madsen and Ragoucy observation. So let's thinking about simple case. G is SL3. Then we take F with nilpotent element in SL3. But F is now, we want to consider classification of nilpotent element. F is nilpotent, so this means the Jordan form of F has only 0 in the diagonal part of Jordan form. So this means we only have 3 choices. One is the biggest Jordan form. My one is a little bit, we want to think F is in lower nilpotent. We want to put F1 in the lower part. But this is a 3 by 3 biggest Jordan form. The middle one is 2 by 2 and 1 by 1. And the last one is 1 by 1, 1 by 1, 1 by 1. So this corresponding to partition of 3. In general, SLN, any nilpotent element can be classified by partition of N, like this. And the left one is called principal. I explained that. The middle one is subregular. It's corresponding to Bershadsky-Polyakov. Last one is 0. 0 is nothing.
Can 0 be used right?
0 is just affine vertex algebra. 0 is affine vertex algebra. Yes. So that means essentially we have obtained 2 different W algebra. One is a principal W algebra of SL3. It's a Mochikov algebra. And the subregular W algebra SL3 is Bershadsky-Polyakov algebra. Okay. So Madsen and Ragoucy consider interesting reduction. So we starting affine SL3. We have principal reduction. It makes principal W algebra. And the subregular reduction, we obtain the Bershadsky-Polyakov algebra. But Madsen and Ragoucy consider reduction from Bell-Shadowsky-Polyakov to get the Marchikov. So they consider cohomology of W-algebra. The statement is a principal W-algebra SL3 obtained as a cohomology of Bell-Shadowsky-Polyakov algebra. This means that they think they commute this diagram. So this is a very interesting observation. So the question is why this happens? What happens? The second question is how about generalization of this property? So our goal is we want to prove this statement, and we want to find the generalization of this statement. In that case, we use reduction by state at this point. But of course, to find generalization in a affine theory, it's so hard because any algebra is so complicated. So the best way is to consider generalization in the other case. For example, finite W-algebra or more commutative case. So to understand this property, we want to consider a family of W-algebra. I mean, finite analog or classical analog from W-algebra. So to get such a finite analog, we introduce the algebra theory from the vertex algebra. So if V is a vertex algebra, we can define V as some quotient of V. A quotient is spanned by B dot B. It's spanning set of A dot B, and A dot B is some product defined by vertex operator. And the point is this V has a structure of associative algebra, and it's called Z algebra. And the point is if you consider simple module of vertex algebra B one-to-one corresponding to simple module of this Z algebra. So this means, of course, if you want to consider all category, it's completely different. But if you only concentrate on simple modules, we have one-to-one correspondence. It's very nice. This theory is called the Z theorem, and this is a very nice development in the representation theory of vertex algebra. So I give example. If V is a affine vertex algebra, this Z algebra is just a universal enveloping algebra of G. It's very nice. But this is by Igor Frankenson. And the question is, what about affine W-algebra? It becomes UGF. This UGF is finite W-algebra. So this is introduced by Pleme originally, and also appear in Wei Nansen talk and also Honmei's talk, the connection between the Yangian. And this is defined by also some BRST reduction on the universal empiric algebra of G. Of course, F equals 0. This is just the universal empiric algebra of G. But F equals principal, it's isomorphic to center of universal enveloping algebra. This is known as a constant theorem. But if you take F as a rectangular case, this is called some quotient of Yangian. It's just a case. You quotient by an infinitely many generator, it becomes a finite generator algebra. It's called introduced Cherdonic by some level L. This proved by Ragoucy solver, but motivated with work, Bland and Fleischer found a very nice connection between Yangian and finite W algebra. They think G is SLN, but F is any nilpotent element. They show that the finite W algebra obtains some quotient of subalgebra of Yangian. It is called shifted Yangian. This problem also studied more another case. For BCD type, Brown considered rectangular nilpotent element and showed that it obtained some quotient of twisted Yangian. Maybe we now also know maybe. And super case, type A studied many people, but now it's also known as any nilpotent element can be obtained some quotient of subalgebra of super Yangian of type A.
All of them are dual algebras, right?
Yeah, this is the old algebra theory. So affine theory is only a few examples known. Affine theory, if G is SLN, F is principal, it's obtained as a quotient of Daha. It's given by Schiffman and Baselo. But such a case, principal case, Daha is thinking about affine Yangian of GL1, right? So this means our expectation is if you change F, then we obtain the quotient of subalgebra of affine Yangian of SLN. It's somehow more complicated algebra than Daha, but I don't know the connection. Yeah, if you want to go fine, it's more complicated. I don't know. There's no general theory other than principal case. Anyway, this is very nice. But we want to cheating or simplest example. So to get the more simplest one, because this is still in general F, this is non-commutative. We want to get commutative one. So if you want to thinking about PBW filtration on the universal empiric algebra, This gives some filtration, and it's isomorphic to symmetric algebra G, but also you can identify this is a coordinate ring of G star. So, but this filtration is commutative, means that it becomes Poisson algebra. So this means the G star is a Poisson variety. Then this symplectic leaf is well known as a quadjoint orbit. But finite W-algebra case, we also have a canonical filtration called Kazdan filtration, and associated graded space can be identified with some coordinate ring of SF, and this SF is the name of a Slodowy slice. This is transversal slice, and I introduce the next slide, but point is this coordinate ring of Slodowy slice also obtained as a BRST reduction of a coordinate ring of G star. This is the analog of finite W-algebra case. Okay, this is a more commutative example. So now I will give definition of Slodowy slice here. So if f is non-zero, we can apply Jacobson-Morozov theorem, imply that we find SL2 triple inside G. This SL2 triple contains our choice of f. So that means this statement is non-trivial. But this SL triple is in some sense unique. It's unique up to conjugation. So then we can define SF as a f plus centralizer of E inside G. But we want to identify G and G star by Killing form. So we want to think it is a variety of G star. Then I want to explain the Poisson structure on this Slodowy slice. So to understand Poisson structure, we introduce a Hamiltonian reduction to define this Slodowy slice. So now we take H as now Cartan subalgebra. Now this is my size H is commutative. And small h is element in H. And if H want to call good pair, it satisfies these three conditions. First of all, adjoint H is degrading by eigenspace is integer, and F is G minus 2, and adjoint F mapping Gj to Gj minus 2, satisfying some injectivity and surjectivity depending on J. But somehow, if H is taking some semi-simple element in SL2 triple, its property comes from representation of SL2. But in general, we have more choice. But anyway, we take some of it. This has been classified by Lashley-Cat for the algebra case, but the super case also classified by White. It's very nice. So using this condition, we define skew symmetric form on G1. By definition, is pairing F and bracket with AP by Killing form. My bracket, the pairing means Killing form. But it satisfies the invariant property. So that means this maps FA pairing to B. But A is G1, then FA is G minus 1. So this means this pairing is G minus 1 and G1. But the G minus 1, G1 is non-degenerate pair. So this means this pairing is non-degenerate. So this defines the non-degenerate skew symmetric form. It means this G1 becomes a symplectic form. Then we take Lagrangian L inside this G1. Then we want to introduce small m. This is L plus G more than 2. This nilpotent subalgebra is, we fix this nilpotent subalgebra in later. Example, if f is a principal, this m is just n plus, this upper half subalgebra. In any principal case, this m is just n plus. And f is a subregular in SL3, this becomes smaller subalgebra, smaller upper half subalgebra. It's like this. So this is our example for m. You forget all definition, but at least we can define such a m associated to f. Okay. Then we take exponential small m. It's like large m. This is unipotent, and this acts on the G star by quadjoint action. But this is known as a Hamiltonian. The momentum map is we identify G star to G. This is just a pairing, and we want to write chi the pairing by f. We want to think it is a function on m, and
For any Slodowy slice,
any Slodowy slice. I did not assume any condition on f. So Gang-Ginsburg shows that this Slodowy slice is identified with mu inverse chi quotient by m. So this is a Hamiltonian reduction, also appear in the talk of Ivan Sechin. And Poisson structure is obtained from this construction.
Pyramid had something like this too, right? Pyramid, right?
Parameter of what?
Pyramid, one of the greatest.
Yes. I mean, it depends on, we choose chi, but of course we have done. So of course, principal case maybe this is a well-known construction of center center. Adler constant, I don't remember that. Yeah, but this is somehow generalization for principal case. Anyway, so this gives the Poisson structure for this size. So we want to study this Slodowy slice, motivated from the problem of Madsen and Ragoucy. So to do that, we introduce reduction by stage. This is a more general framework. If you take X is a Poisson variety, but some Hamiltonian action by M2, and M1 is normally subgroup of M2, then we can consider Hamiltonian reduction of M1 and also Hamiltonian reduction of M2. The first line is the Hamiltonian reduction of M2. Then we get some new Poisson variety. The middle one is Poisson Hamiltonian reduction by M1. Yes, yes. Yes, we restrict this reduction. But under some nice condition, it also depends on choice of X, on choice of M1, M2. Sometimes we can define Hamiltonian action of quotient M2 quotient by M1, then the reduction of this middle one to get the last one. This is called reduction by stage because we get this last Poisson variety by stages. So that is the reason why it's called reduction by stage. And then we want to apply this case for Slodowy slice. I mean, this X choose G star. This problem has been studied by Morgan in his PhD thesis. His conjecture is if G is SLN, and we want to take F1, F2, satisfying that nilpotent orbit, satisfying ordered condition. It means OF1 is contained in the Zariski closure of OF2. Then the Slodowy slice of F2 is obtained as a Hamiltonian reduction of Slodowy slice of F1. But he only proved M equals 3 case. Somehow he stated very somehow naive conjecture. But anyway, he proved S3 case. He considered principal and subregular. He showed that the principal one is obtained from subregular by some Hamiltonian reaction. But this is, you see, analog of Madsen and Ragoucy observation, right? Madsen and Ragoucy starting affine SF3, then principal one is Zamochikov, subregular one is Berezovsky-Polyakov. So this picture is completely finite analog.
Can I ask for higher rank? There's many more choices.
Of course. So my problem is want to generalize this problem. Yes, yes, yes.
To have a conjecture that if something belongs to something, it always is a second reduction.
Yes. In fact, I prove generalization of the statement. I do not care about G and I do not care about F, but satisfying some condition. I explained that. Okay. Okay, let's start your question. I mean, reduction by stage for Slodowy slice and finite W-algebra. To deal with, we assume some condition called the step condition, because we make a step to get a stage. So we take F1, F2 as nilpotent element, and H1, H2 is semi-simple element from same kind of term subversion. It means H1 is to commute. Then we want to write the GJ1 is grading by adjoint H1, GJ2 is adjoint H2. Then we can make a nilpotent algebra. We want to write M1 and 2, and the Gang-Ginsburg theorem. A Slodowy slice of F1 obtained Hamiltonian reduction. Slodowy slice of F2 is obtained Hamiltonian reduction. Then we can introduce definition of step toward F2, F1. H1 is very complicated patching condition because we need to make a reduction by stage. We need some patching condition. But at least you can forget this condition because I will explain example satisfying this condition. So first of all, the consequence of this condition implies that the nilpotent orbital F1 is contained in the Zariski closure of F2. This is assumption and mentioned in Morgan. And also M1 is the ideal of M2. So this means the exponential of this one is normal subgroup. And yes, yes, yes. Yeah. And the M0 is written explicitly and under this condition. And also you can find the Hamiltonian M0 action on the Slodowy slice of F1. And our theorem, joint work with Thibault Juillard, is assumed that this step condition is satisfied. then Slodowy size of F2 is obtained as a Hamiltonian reduction from Slodowy size of F1. And also, using this classical case, we obtain that the finite W-algebra case is still same, obtain the same result. I mean, finite W-algebra of GF2 is obtained as some quantum Hamiltonian reduction of finite W-algebra of F1. It's very nice. Then the question is, how many examples we have? We gave example for many cases. For example, G is SLN, and taking A1, A2 as some integer, and A2 is bigger. And we consider F1 as nilpotent corresponding partition A1, 1, 1, 1, 1. F2 is A2, 1, 1, 1, 1. This is called hook type nilpotent because corresponding Young diagram looks like hook. That's the reason. Then F1, F2 satisfies the step convention. Then we obtain the theorem. In fact, this contains a rectangular case, I mean principal case and the subregular case. So then this covers n equals 3 case. They completely cover all cases. But also we have a non-hook type, where we can find such example in SL4. I mean, F1 is hook type, but F2 is a rectangular type, F2, 2. But we obtained this, we found a nice step condition. Also, we have a B type, it's F1 subregular, F2 principal, and the C type, we have some it's not rectangular, it's somehow short nilpotent, but F2 is a principal. We obtain the same result. Still, we have G2 in using Barakata labeling. F1 is A1 tutor, F2 is subregular. We can check this.
You can write a computer program and we'll create all.
Yeah. I don't know the classification, but at least we find many examples. I don't know. It's called complicated condition, but anyway, we found many examples. It's a very nice story. So the question is now go to affine case, right? But before that, I want to give one application to the representation theory of this result. So if you want to write chi as a pairing of F, and if you want to write I chi as ideal generated by U minus chi U, then I want to write Q chi, the quotient. Then a joint invariant has still associated algebra. It's this isomorphic to finite W-algebra. This is the original definition plan. But if you use this definition, we can think in a Whittaker module of G for corresponding to our choice of chi. And then we consider Whittaker space, Whittaker E. This space is spanned by Whittaker vector. But the point is that by definition, by this construction, this Whittaker space becomes a module of finite W-algebra. On the other hand, we want to consider a category of finite W-algebra. We can consider induction using this Q chi. You can show this module is also a Whittaker G module. Then we have.
For a second, the 18 number into the previous page. It's just too fast.
Okay.
Would we take your. And there are Jou modules, UGF, there are Jou algebras, right?
Yeah, so this one is defined by the algebra or BRT reduction. But this is different, some invariant of some quotient of finite W-algebra. But you can show this isomorphism using the procedure of the spectral sequence. And the point is this Q chi is a quotient by I chi, but this Whittaker condition says this is compatible with our idea. That's the reason, okay? So anyway, we have some functor between them, from the category of Whittaker module and the category of finite W-algebra module. And this is, in fact, we can show this is a categorical equivalence between them. This is called Scriabin equivalence because stated by Scriabin, but precisely the proof given by Gangin's. But anyway, this is called Scriabin equivalence. But using our reduction by stage, we can show a reduction by stage version of this equivalence.
Like Jou theorem, right? The Jou algebra gives vertex algebra.
Yes.
This is some counterpart, right?
Yes. So this one's finite W.
Are you approaching this later in your talk?
Not. Of course, we want to think such application, but I'm not prepared so well. But anyway, at least we prove that the finite W algebra case, we can get similar algebra. The point is the first one is standard Scriabin equivalence, but the middle one is Whittaker category of Whittaker module of finite W algebra. But still, we have equivalence of category. This is a statement of Scriabin equivalence of this stage. And recently, Massey also considered this equivalence, and she think about Goodwin's translation factor, and she proved that compatibility with them. Anyway, this is very useful to study analysis. Okay, so finally I go to the affine story. The affine story is, we recall affine W-algebra is defined by some cohomology of affine vertex algebra. So this means we want to claim the second line. If W-algebra F2 obtain the BRC reduction of W-algebra of F1. So this means we want this morphism. But you see, one is a cohomology, the other is a cohomology of a cohomology. It's so difficult to find such a good map because we require this map is a morphism of a vertex algebra. So, if you consider different N1 and 2, this is the more technical part. If you consider N1 and N2 and consider large N1 is exponential, point is this N1 is bigger than our M. But point is we consider a nilpotent orbit OI, we consider twisted version of Gang-Ginsburg theorem. We replace M1 instead of N1, this bigger one. So this space is a little bit bigger. Anyway, we can find such a different BRC Hamiltonian reduction. Then we can written in terms of cohomology for this reduction. And finally, in fact, using this new reduction, we obtained a similar result for finite W-algebra case. Then our claim is we still have the same result for a fine W-algebra case. But point is, if using this BRC reduction, we can find a good map corresponding to the original statement. I mean, if this claim...
Normally, at this place, we say spectral sequence degenerates, right?
Yes. In fact, this case, the first one is we need to construct spectral sequence. But this case is just double complex. So that is somehow easier to treat before. Anyway, so we only need to show this claim. But to claim, we need one conjecture. We need associated graded is still isomorphic to this one. Now in progress, we can show this conjecture only Fuchs type. But at least this Fuchs type contains the principal subregular. Then our theorem is a step condition is satisfied. We can and also conjecture is true. We obtained this isomorphism. Sorry, I extra 2 times, but I finished my talk. Thank you.
Thank you. It seems quite. You have already asked many questions, but maybe still there are questions. Yeah, we have still much time.
Oh, really?
Anybody?
You promised to say little something about the fine case. Do we have time?
Ah, okay.
Affine is toroidal or whatever, right?
Okay, so...
Did you promise
yes, my expectation is this result also for the deformed W-algebra case. It's somehow additional promise. I'm not sure. How about, do you have... Yeah.
We don't have much time.
Yeah, so I don't know. There's a definition of deformed W-algebra of other type F, but if you have such a definition, we expect the same result.
Okay, so maybe we can discuss at lunchtime. So let's thank the speaker again.